Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to look at solving systems of linear equations using determinants. Before we can use determinants to solve systems of linear equations, I need to define what a determinant is. So they were developed by a mathematician named Leibniz a few hundred years ago, and a determinant represents a quantity of arrangement of numbers. It has to be a square arrangement, and there has to be equal number of rows and columns, and the notation that we use to represent determinants is these two lines. When they're just the lines, it represents a value. It represents an operation. And the definition of that value or that operation is you take this product here, so 1 times 4, and you subtract this product here, 2 times 3. So that's the definition of a determinant. So that's 4 minus 6. So the value is -2. That's all that it is. I want to mention that I call this the principal diagonal. And this is the secondary diagonal. Doesn't matter so much when I have a determinant of the second order, so 2 rows, 2 columns, but it becomes more important when we get into determinant of the third order. Well, another mathematician named Cramer figured out how we could use determinants to solve systems of linear equations, and it's actually a very slick method, and I find that students often prefer the method because they don't have to mess around with substitution or algebraic or addition subtraction procedures. They just plug into Cramer's rule. So I'll show it to you, and then you can decide if it's a method you prefer or if you like the algebraic methods for solving systems of linear equations instead. So let's take a look at an example. This first example is actually one we've done in the previous 2 videos, so I wanted to do it again. And I've colored the coefficients for x in red, the coefficients for y in blue, and my constants in green. In order to use Cramer's rule to use determinants to solve systems of linear equations, you have to have them all in the same order. So if the x term is first in your first equation, it has to be in the second equation. And the other thing, you have to have your constants on the other side. So make sure you have one variable, then the other variable, and then the constants on the other side of the equal sign. When I do this initially, it might be a little bit confusing, but I'm hoping that the colors help you understand. When you're solving for a variable, so we're going to start off with x, the answer or the solution for x will actually be the quotient of 2 determinants. The denominator will be the determinant of your coefficients for your variables. So 4, 2 for the x coefficients, and then we have 5, -3 for the y coefficients. And we'll evaluate that in just a minute. The numerator for the solution for x will be a determinant, but we replace the coefficients for x with the constants. So in this example, I have -15 and 9. So I replace the coefficients of x, which are 4, 2, with -15, 9, and the rest of it stays the same. So I still have 5 and -3. Now we evaluate. So our numerator is going to be -15 times -3 will be 45, minus this diagonal, the secondary diagonal, 45. Well, I know that's a 0, I don't need to proceed. However, I will demonstrate. The denominator will be 4 times -3, which is -12, minus 2 times 5, which is 10. So 0 over -22, which is 0. And we found that before, x was equal to 0. To find y, we can use determinants. And one really nice thing is that when we're finding y, the denominator will be the same, because the denominator for y will be the same determinant as the denominator for x. It's the determinant of those coefficients. So it's going to be negative 22. To find y, because I'm solving for y, I replace the y coefficients with the constants. So I keep the x coefficients. Because I'm solving for y, I don't use the y coefficients, I use the constants. And now I can evaluate the numerator. So I have 4 times 9, which is 36, minus 2 times negative 15, so negative 30, over negative 22. So I'm going to get 36 plus 30 over negative 22, which is 66 over negative 22, which is negative 3. So y is equal to negative 3. We obtained those solutions previously, so I'm not going to bother checking, but you could check, put those two values into both equations to make sure they make both of them correct. So it seems like a lot of work setting up your determinants, but it's fairly easy to evaluate, and you're not taking your equations and multiplying one equation by this value and another equation by this value and finding what that value is to begin with. There's a lot, I think, more thinking and manipulating when you're doing it algebraically, whereas when you're doing determinants and you get practice with it, it just, boom, you set up your determinants, the numerator, the denominator, and evaluate. For your other variable, it's the same denominator. You don't have to evaluate that again, but you do have to do the numerator. You could combine algebraic methods with determinants. Once I obtained the value of 0 for x, I could have then gone and put that value into either equation to find y. So you can combine determinants with algebraic methods as well. But I'm just going to stick to determinant method in doing these solutions. Feeling comfortable? Let's try another one. Again, this is a question we did in the last video, and we did it by adding and subtracting or elimination method. I'm going to do the same question, this time using determinants. So we set up our first variable we're going to solve for. Once I've made sure everything's in the correct order and my constants are on the other side of the equation, I've got my m term, then my n term in both equations, and my constants on the other side, so I'm good. I'm going to solve for m first. So the denominator is always the determinants of your coefficients, and keep the order. So I have 2, 3, and then I have negative 3, negative 2. That's where I see a lot of students have problems, is forgetting about the sign or getting the sign mixed up. Our numerator will be the same, except we replace this column. Because we're solving for m, these are the coefficients for m, we replace those with the constants. But negative 3 and negative 2 stay. So there's our determinants. Now we just evaluate. So our principal diagonal, 4 times negative 2 is negative 8, minus negative 2 times negative 3 is positive 6. In the denominator, 2 times negative 2 is negative 4, minus 3 times negative 3 is negative 9. So that's going to be negative 8 minus 6 is negative 14. Negative 4 plus 9 is 5. That was quite a bit faster than using the algebraic method we used in the last video. So I think students will come to like this, especially once you understand it, understand Cramer's rule, and keep your order consistent. So start off when you're doing these, do the color coding, because that's going to help you keep track of your coefficients and make sure that the columns are correct. Let's do n. To find n, I already know the denominator is 5. I don't need to reevaluate it. We just need to find the numerator for n. Because we're solving for n, we're going to replace these coefficients. But I leave the 2, 3. But n coefficients are those ones. I replace those with the constants. And now we can evaluate. So I have 2 times -2, which is -4, minus 3 times 4, which is 12, over 5. -4 minus 12 is -16 over 5. Even faster to calculate n, because we just had to do the numerator. We already had the denominator. So a fairly quick, easy method once you get the rule down. I'd like to do this example. We did it in the last video. These are actually the same line. If you took this linear equation and multiplied by 2, you would get this. So they're actually the same line, which we know is a dependent system. We're not going to get one solution. Now, you will know that it is either a dependent or inconsistent system if you get a denominator equal to 0, which is going to happen here. If I do x equals, and I take the determinant for the denominator, will be my coefficients for x, followed by my coefficients of y, and if I were to evaluate that, I'm going to get 2 minus 2, which is 0. You know that there's an issue if you have a denominator equal to 0. So it tells you either this is a system that's inconsistent or it's a dependent system. In order to know which one, you would have to evaluate the numerator. So we replace, I'm solving for x, I replace my x coefficients with the constants. Keep the y coefficients and evaluate. 5 times 2 is 10, minus 10 times 1, 0. If you get a numerator and a denominator equal to 0, this is a dependent system. Same line. If it's an inconsistent system, you will get a denominator equal to 0, but you'll get a number other than 0 in the numerator. And when that happens, you know that they're parallel lines. It's an inconsistent system. So that could happen if I change this. They're not the same line anymore, but they are parallel. So you still have a denominator equal to 0, but your numerator is a number other than 0. If this happens, this means it's an inconsistent system. Which means that they are parallel lines, which means there's no solution. So I usually evaluate the denominator first. If it's 0, I know that it's either inconsistent or dependent, and I know that I'm not going to have one solution. So it doesn't happen very often, but in case it does, be aware of what that means. You now have 3 methods for solving systems of linear equations. You can either do it algebraically through substitution or elimination, or you can use determinants. I find that having knowledge of all 3 is useful because certain methods work better with certain systems, but you may end up preferring one over the others. That concludes 2 equations, 2 unknowns. In the next videos, we're going to look at 3 equations in 3 unknowns. Until then, take care.